Okay. Hello, everyone, and welcome to a new lecture of our course on processing in memory. Today, we have an invited speaker. Well, he's not really an invited speaker. He's Geraldo Francisco de Oliveira. He's a PhD student in the Safari Research Group. He's doing his PhD with Professor Onur Mutlu and working on different aspects of processing in memory. He has actually very interesting projects, both in the two main trends that we identify in processing in memory. You remember one of them is processing near memory, the other one is processing using memory, and that's the reason why we may have him again giving another lecture in an upcoming week. The work that he is going to present today, it was published last year, and it's a methodology to identify and evaluate data movement bottlenecks in processor-centric systems. So yeah, feel free to ask any questions during the presentation. Also, if you are attending in YouTube, feel free to ask any questions and we will answer them as soon as possible. Geraldo, when you're ready, please go ahead, and thank you very much for giving this lecture.
Thanks so much, Juan. So as Juan said, I'm a PhD student here in Safari, and today I'm going to be talking about our work on benchmarking and create methodologies for identify data movement bottlenecks, targeting specifically near data processing systems. Okay, so let's get started. So I'm going to start with a quick executive summary of what this paper is about. So as probably we know at this point, data movement is a major bottleneck in today's systems. However, so far, it wasn't clear to us or to the in the literature in general, how to identify different sources of data movement bottleneck in application and the most suitable data movement mitigation mechanism, for example, caching or prefetching or new data processing for a given data movement bottleneck in a systematic way. So based on that, the goal of this work is twofold. First, you want to design a methodology that can identify the sources of data movement bottleneck in a given application, and also compare compute and memory-centric data movement mitigation techniques. And the key approach that you're going to take is to perform a large-scale application characterization so you can identify key metrics that reveals the sources of data movement bottleneck. The main contributions of this work are four. So the first one, you have the experimental characterization of over 77,000 functions across 245 applications for different application domains. Then based on this characterization, we drive a methodology that can characterize applications based on data movement bottlenecks and their relationship with different types of data movement mitigation techniques. Then we collect the data that we generate with by applying our methodology in the DAMOVE benchmark suite, which is a benchmark suite with 144 functions classified into 6 different classes of data movement bottleneck. And finally, we take our benchmark suite, DAMOVE, and we apply 4 case studies to highlight how our benchmark suite can be used to study open research problems on data processing. And our DAMOVE benchmark suite and our simulation infrastructure that I'm going to show next is open source and available in the following GitHub. So feel free to download, use it, and hopefully it's useful for your research. So this is the outline for this talk. So first, I'm going to briefly talk about data movement bottlenecks. Then I'm going to give a methodology overview, and then we are going to follow our methodology in 3 steps: application profiling, locality-based clustering, and memory bottleneck analysis. And finally, I'm going to present the case studies. So we start with data movement bottlenecks. So data movement became a problem in modern systems. So we have been seeing this in this PNS pinkers is a recurrent topic in this PNS class, for example. So data movement bottleneck is going to happen, or is going to become a problem for several reasons. I'm going to list 3 reasons over here, but it's not limited to that. So the first one is that the application there is no enough data locality inside the application to leverage the cache hierarchy of modern CPU systems. The second one is that the DRAM system cannot provide, or the memory cell system cannot provide enough memory bandwidth for a particular bandwidth intensive application, or third, that overall accounting for all of the latencies involved in the memory subsystem, which adds up and impacts the application application's execution time, or dominates the application memory execution time. So high-performance computer systems or compute-centric architectures have implemented several different approaches so far to try to alleviate memory data movement bottlenecks. Those approaches range from deep cache hierarchies to hardware prefetchers. However, such approaches cannot fully mitigate data movement bottlenecks in a particular application. And then alternative solution is to use memory-centric architectures. In memory-centric architectures or new data, or example here, new data processing architecture, the system moves elements or elements for computing elements to inside or nearby the memory subsystem. In this way, the system can avoid the costly off-chip linking interconnect, which increases energy and also leads to performance bottlenecks, while benefit from the high DRAM bandwidth that is provided when you are inside the DRAM chip itself. And as I said, new data processing one of the main examples of memory-centric architectures today. So the main goal of processing memory then, as a memory-centric architecture, is to mitigate data movement bottleneck. And new data processing have been, is not a new idea to be said. So there are proposals from the 1970s, for example, that already propose new data systems. However, only recently, the industry have started catching up with the advance of new data processing techniques. So in this, I'm going to highlight two architectures here that has already been covered here in this class. So the first one is the UpMem architecture, which was developed by a company of the same name and demonstrated in 2019, which is a near DRAM bank processing system for general purpose computing, which can achieve up to 0.9 tera operations per second of compute throughput. Another example, we have SimDRAM, FIMDRAM, which is also a near DRAM bank processing architecture from Samsung, released in 2021, which targets neural network operations. This system can achieve 1.2 teraflops of compute throughput. So right now we have these two examples here, but since 2021, we have seen more examples from industry. So we have, for example, new data processing systems from other companies like Alibaba, other architectures from Samsung, or other neural network-based architectures from SK Hynix. So as you can see, that's a really timely time to study processing memory architectures. So then the question becomes when to employ new data processing systems or architectures, right? So as the previous slides have shown, that new data processing can be either general purpose or for a particular workload. There are many works in the literature that applies new data processing for different application domains. For example, graph processing, mobile consumer workloads, neural networks, DNA sequence mapping, databases, time series analysis, and much more. So the one thing that is common related in all of those works is that they rely on different methodologies to identify memory portions of the application that suffers from memory bottlenecks, and then they use such methodologies to infer that such functions could benefit from data movement bottleneck. However, as I'm going to show next, none of those methodologies or models are comprehensive enough to identify memory bottlenecks and new data processing suitability. So this happens for several reasons, but in general, the problem is that these models are built to target into identifying specific sources of data movement bottleneck in application. For example, bottlenecks caused by bandwidth or bottlenecks caused by latency, and often their definitions of compute bound or memory bound are not enough to indicate new data processing suitability, because those models were not designed for having new data processing in mind. They were designed thinking having the compute-centric approach in mind. So I'm going to illustrate with two quite common models to identify memory bottlenecks that many prior works have been used to also infer that application or function can benefit from data processing. It's their inefficiency. So the first one is a roofline model, and the second one is using high level, the number of less level cache misses per kilo instructions as an indication of NDP suitability. So first I'm starting with the roofline model. So the roofline model is a simple model used to identify if application is memory bound or compute bound. So this model has two main lines. So the x-axis, there are two main axes. So the x-axis of the plot is going to define the arithmetic intensity of the application, which is calculated as the number of operations the application executes per byte access. While the y-axis is going to define the performance of the application in giga operations per second. So and then it has two main lines. They characterize the application and the system. So the first line, which is called compute roof, it is defined as the peak system throughput. Applications that lie below this curve are called compute bound applications, and often prior works have said that compute bound applications are not suitable for any data processing acceleration. The other line is called the memory roof and is defined as the maximum DRAM bandwidth times the arithmetic intensity of our application. Prior works have shown that application that lies below this memory roof are memory intensive and then can benefit from the data processing offloading. So we use this model with more than 40 applications from many different application domains, which we are going to analyze later. So we compare such applications benefit from a general purpose data processing architecture and a baseline CPU. In the plot, we classify applications in 4 different groups. So the first group is the applications that run fastest on the CPU, compare on running on the NDP systems, run faster on an NDP system, compare on running on the CPU, have similar performance on the CPU and NDP system, and which performance depends on system configuration. So for example, the number of cores in the system. So based on that, we make the following observations. First, we observe that memory-bound applications do benefit from data processing as prior works indicates. Second, compute-bound applications do not benefit from the data processing, also as indicated by prior works. However, we observe that there are some memory-bound applications that can also not benefit from the data processing or benefit from it in particular configurations, as for example, a different number of core counts. This behavior can also happen for compute-bound applications. Therefore, we conclude that the roofline model cannot accurately account for the NDP suitability of all memory-bound applications. Next, we are going to analyze another metric utilized to identify the data process suitability. So many prior works have said that an application with a high less level cache misses per kilo instructions, high here usually means a value larger than 10, can benefit from the data processing. So we check such assumption by evaluating the speedup provided by the NDP and a general purpose NDP system for a large number of applications, which we have here in the y-axis, and the applications in PKI in the x-axis. So we make the following observations. First, applications with high MPKI do benefit for data processing, as prior works has shown. Also, applications with low MPKI are faster on the CPU system. However, we see that there are another group of applications with low MPKI that can either be faster on an NDP system, have similar performance on the CPU or NDP system, or its performance depends on system configurations. Therefore, we also conclude that using less level cache misses per kilo instructions cannot currently account for the NDP suitability of memory-bound applications. Therefore, we summarize this experiment with these two methodologies by concluding that there is no available methodology that can comprehensively identify data movement bottlenecks and also correlate these data movement bottlenecks with the most suitable data movement mitigation mechanism. Based on that, the goal of this work is to develop a methodology that can identify the sources of data movement bottlenecks and also compute and memory-centric data movement mitigation techniques. Now I'm going to present the methodology that we developed in this paper. So we developed a new methodology that can characterize data movement bottlenecks and also the suitability of different data movement mitigation mechanisms. We use two main profiling strategies. So the first one, we use architecture-independent profiling tools, which can characterize the memory behavior of application independently of the underlying hardware properties or characteristics. The second one, we use architecture-dependent profiling tools, which can evaluate the impact of the system configurations on, for example, the size of the memory hierarchy or hardware prefetchers on the memory behavior. Our methodology has three main steps. So it takes as inputs application source code and its input datasets. In the first step, we use hardware profiling tools to identify memory-bound functions across many applications. This step allows for a quick first-level identifications of many applications that suffer from memory bottlenecks and functions that cause these bottlenecks. We then utilize a new simulator called the MoveSim to collect key metrics to execute performance analysis of the functions identified in step 1. In step 2, we use architecture-independent profiling tools to collect metrics that can provide insights about the memory access behavior of the memory bottleneck functions. In step 3, we collect architecture-dependent metrics, analyze the performance and energy of each function in application, when each one of the each application runs on 3 different candidate data movement mitigation mechanisms that we apply in this system. Then by collecting the data in step 2 and step 3, we classify the applications using 4 key metrics into 6 different classes of memory bottlenecks. And each class of memory bottleneck correlates with one particular data movement mitigation mechanism. So next, we are going to see each one of these steps in detail, starting with step 1. So the goal of the first step is to identify functions in application that suffer from memory bottlenecks. So this step is more like a filtering for us to guide step 2 and step 3. So to profile the applications identifying functions that suffer from data movement bottlenecks, we use hardware profiling tools. We leverage hardware profiling tools, and in this work specifically, we use the Intel vTune tool to identify memory-bound functions. The Intel vTune provides a metric called memory-bound, which is defined as the percentage of CPU pipelines lost. They are not utilized because of memory stalls, and we use this metric to define if application could benefit as a first indication of if application would benefit from an NDP or not. So we are going to look at this next. We're going to look at the second step. In step 2, we aim to analyze the application memory characteristics, as for example, locality. Thus, we could understand how it affects the components of the memory system, as cache behavior or prefetching. To this end, we evaluate 2 key metrics. So first, my mouse is not working. Okay. So first, we are going to evaluate the spatial locality of application. For this, we collect the memory trace of application to build a histogram called stride profiling, where each bin in the histogram stores how many times each stride appears in the memory trace. In this example that I have over here, the stride between the first access address and the next access address is equals to 1. We increment the stride profiling histogram in bin 1 to indicate such stride has been observed. Use the stride profile histogram to calculate the cumulative distribution of the stride profiles, which represents the final spatial locality value. A spatial locality value close to 1 is caused by large stride values or random access, as shown in this example. In such case, we say the application has low spatial locality. A spatial locality value close to 1 is caused by a completely sequential access pattern. In such case, we say the application has high spatial locality. Similarly, we evaluate how much temporal locality application has. For this, we collect the memory trace of application to create a histogram called reuse profile, where each bin represents the number of times a memory address is reused. For each memory address, we increment the bin that represents the corresponding number of repetitions. In this example here, memory address A is reused 4 times. Thus, we increment the reuse profile in bin 4 to indicate such reuse has been observed. We use the reuse profile histogram to calculate the cumulative distribution of reuse profiles, which represent the final temporal locality value. A temporal locality value close to 0 is caused by low data reuse. In such case, we say the application has low temporal locality. A temporal locality value close to 1 is caused by high data reuse. In such case, we say the application has high temporal locality. Finally, we look into the step 3 of our methodology. Why step 2 allows us to understand the inherent pro-application sources of memory bottlenecks? It's important to understand how hardware architecture features can also result in memory bottlenecks. As a result, in our third step, we perform a scalability analysis of the function selected in step 1, where we evaluate the performance and energy scaling for 3 different system configurations. The scalability analysis makes use of 3 architecture-dependent metrics. First, arithmetic intensity, or AI, which we define as the number of fluid point arithmetic operations per L1 cache lines access. Arithmetic intensity is useful to show the computational intensity per memory request of a particular application. Second, we use also like prior works, we use the less level misses per kilo instructions, or MPKI, to indicate the memory intensity of application. And finally, we design a new metric called less to first miss ratio, or LFMR, which is defined as the number of less level cache misses divided by the number of L1 cache misses. This metric can show the benefits from the benefits that the L2 and L3 caches provide for the application. If application has a less first miss ratio close to 1, if the application has close to 1, it means that very few L1 misses hits in the L2 and L3 caches. And the application does not benefit much from the deep cache hierarchy. And most L1 misses needs to be served by main memory. In contrast, if application has a LFMR value close to 0, it means that very few L1 misses generated L3 less level cache misses, and then the application is benefiting for the L2 and L3 caches. The goal of the scalability analysis is to nail down the sources of data movement bottlenecks in a particular application. In this analysis, we evaluate the performance and energy scaling of the application in 3 different system configurations. We collect the key metrics for a bottleneck classification. During the scalability analysis, we simulate 3 system configurations of a general proposed multi-core processor. To this end, we build a framework that integrates the ZSIM CPU simulator with the Ramulator CPU memory simulator to produce a fast, scalable, and cycle-accurate on-per source simulator called the MUSIM. We use ZSIM to simulate the core microarchitecture, cache hierarchy, coherence protocols, and prefetchers. And we use Ramulator to simulate the DRAM architecture, memory controllers, and memory access. The first configuration that we evaluate is of a host CPU with a deep cache hierarchy. The cache hierarchy has a 32 kilobyte private L1 cache, a 256 kilobyte private L2 cache, and a shared 8 megabyte L3 cache. The second configuration is of ND data processing CPU with only a private read-only L1 cache of 32 kilobytes. In our paper, we evaluate a third configuration that includes hardware prefetcher on top of configuration 1. However, we omit such configuration in this talk. The remaining components of the processor configurations are kept exactly the same between the configuration 1 and configuration 2, so we can isolate the impacts of only the cache, prefetchers, and NDP in our evaluations. In this way, we expect the performance and energy difference between the 3 configurations to come exclusively from the different data movement requirement for a particular application. For all configurations, we swept the number of CPU cores in our analysis from 1 to 256, as prior work shows that large core counts are required to saturate the bandwidth provided by modern high bandwidth memories, and because modern CPU need data process and NDP systems can have varying core counts. We simulate a memory architecture similar to that of a hybrid memory cube of HMC device, where the host CPU access memory through a high speed off-chip link. And the NDP core has access to higher memory bandwidth and lower memory access than the CPU core itself. Next, we apply our 3 steps, we are going to apply the 3 steps of our methodology to characterize the sources of data movement bottlenecks over a wide range of applications. First, we are going to apply step 1 to identify applications that suffer from memory application functions that suffer from memory bottlenecks. So we analyze in this work over 345 applications from different domains. Those domains varies from graph processing, deep neural networks, physics, high-performance computing, genomics, and many more. We observe that applications that benefit from new data processing and suffer from memory bottlenecks have a memory-bound metric that we collect from VTune greater than 30% and takes at least 3% of the clock cycles. We observed 144 functions with such characteristics from more than 77,000 functions, which you select, which you divide. 44 functions to apply step 2 and step 3 of our methodology, and 100 functions to validate our methodology and our experimental methodology. Then we go to step 2 of our methodology, which you're going to apply on top of the 44 functions that we selected previously. So we collect the spatial and temporal locality values from the selected 44 functions and perform a locality-based clustering. We use the k-means cluster to create two groups of applications. Applications with low locality, here in orange, and applications with high locality, here in blue. The closer a benchmark is to the bottom left corner of the plot, in other words, the lower the temporal locality and spatial locality displays, the less likely it's going to be that the application can take advantage of a deep cache hierarchy. With this cluster in mind, we conduct our bottleneck analysis. Within the two groups of functions we identify, we use three key metrics, arithmetic intensity, MPKI, and last first miss ratio, or LFMR, and temporal locality to classify the memory bottlenecks of application. Based on that, we find that 6 classes of functions emerge, which I'm going to explain each one in details next. These classes of memory bottlenecks are DRAM bandwidth bound applications, DRAM latency bound applications, applications that with L1, L2 cache capacity bottlenecks, L3 cache contention bottleneck applications, L1 cache capacity bottleneck applications, and computations that are not memory bound or does not experience any particular source of memory bottleneck, and we call these applications compute bound. With such classification, we analyze how the functions in each class correlates with different data movement mitigation mechanisms in terms of performance and energy using our scalability analysis. Next, we look in details about the scalability analysis for the DRAM bandwidth bound applications. Applications in this class have low temporal locality, high last first miss ratio, high MPKI, and lower arithmetic intensity. We make the following observations. First, applications in class 1A exert high memory pressures in the system. It means that they will likely require high memory bandwidth from the application memory system, from the memory subsystem. To understand how such high memory pressure impacts performance, we observe how performance scales when increasing the number of cores. So as we see here in the figure, the host performance scales well until the memory bandwidth saturates at 64 cores. NDP, on the other hand, scales much better due to a large available bandwidth inside the memory chip itself, and the performance gains does not saturate until 256 cores. Therefore, we conclude that DRAM bandwidth bound applications highly benefit from the data processing architectures because they take advantage of the high memory bandwidth available within the memory device. Likewise, we analyze the energy consumption of DRAM bandwidth bound applications when executing on the host system and in the NDP systems. As mentioned before, applications in class 1A has high last first miss ratio, which indicates that they do not make any effective use of the L2 and L3 caches. We observe here in this plot how such inefficiency impacts energy consumption for the host system and NDP systems. We make the following observations. First, as we can see in the figure, the host energy consumption is dominated by L3 cache lookups and high energy off-chip DRAM requests, as we expected due to the high last first miss ratio. Second, NDP, on the other hand, reduces the energy consumption compared to the host, since it avoids the L3 cache lookups and the off-chip memory traffic. Therefore, we conclude that DRAM bandwidth bound applications highly benefit from NDP, low MPKI, and low arithmetic intensity. Applications in class 1B does not make effective use of the cache hierarchy since they have high last first miss ratio, but they do not exert high memory pressure on the memory system in contrast to applications in class 1A. We observe that even though the host performance scales well, the ND data processing performance is always higher. We find that the NDP system performance improvement is due to a reduction in the average memory access time. Memory access time takes longer in the host CPU system than in the NDP system due to the additional latency of looking up requests in the L2 and L3 caches, even though data is rarely present in those caches and going through the off-chip and thus going through the off-chip links. To conclude, Class 1B functions benefit from the NDP system, but primarily because of the low memory access latency that the NDP system can provide. These functions could benefit from other latency reduction and latency energy reduction techniques, such as L2 and L3 cache bypassing or low latency DRAM approaches. Next, we analyze L2 and L1 and L2 cache capacity bound applications. Applications in this class have low temporal locality, decreasing less first miss ratio with the core count, low MPKI, and low arithmetic intensity. We find that the behavior of this function in this class depends on the number of cores they are using. The decreasing less first miss ratio implies that L2 and L3 caches become efficient when increasing the number of cores. We analyze how this impacts performance. At low core counts, the NDP system outperforms the whole CPU system. With a low number of cores, the application have medium to high less first miss ratio and behave like Class 1B applications, where they are DRAM latency sensitive. However, as the number of cores increases, the whole CPU system begins to outperform the NDP system. So we see that this is because the core, as the core count increases, the aggregate L1 and L2 cache size available to the whole CPU system also increases, which reduces the number of miss rate, the number of misses in both L2 and L3 caches. To conclude, we find that the primary source of memory bottlenecks in Class 1C is limit L1 and L2 cache capacity. Therefore, while the NDP system improves performance at low core count, the ND data processing system does not provide performance benefits across all core counts for Class 1C functions. Now, you analyze applications bottleneck by L3 cache contention. Applications in this class have high temporal locality, increasing less first miss ratio with the number of cores, low MPKI, and low arithmetic intensity. The increasing less first miss ratio indicates the L2 and L3 caches turning efficient when we increase the number of cores. We observe how such inefficiency impacts the host and NDP performance. At low core counts, the functions do not benefit from an NDP system. This is because at low core counts, these functions make reasonable good use of the cache hierarchy. As the number of cores increases in the CPU baseline system, the NDP system starts to outperform the CPU system, the baseline host system. This is because Class 2A functions are bottlenecked by cache contention. At high core count, this contention reduces the effectiveness of the caches and causes the LS first miss ratio to increase it near to 1, thus increasing the number of memory requests that needs to be served by DRAM. With the less level caches becoming essentially ineffective, the NDP system greatly improves performance over the whole CPU system. We conclude that applications in this class are bounded by the cache contention. At high core counts, those high locality applications becomes DRAM latency bound. Now we analyze applications bottlenecked by L1 cache capacity. Applications in this class have high temporal locality, low less first miss ratio, and MPKI and arithmetic intensity. The low less first miss ratio, MPKI, and high temporal locality indicates that such applications make effective use of the cache hierarchy and also have low memory intensity. Also, the low arithmetic intensity indicates that such applications execute few operations per byte loaded from the memory hierarchy. We observed that the host performance and the NDP performance scales in a similar fashion, even though the NDP has less on-chip caches. Such a reduction on SRAM does not hurt the performance when moving to the NDP system, since the L1 cache present in the host and NDP system dominates the average memory access time for such applications. We conclude that even though NDP system does not mitigate any memory bottleneck for these applications, it can still be useful for reducing the overall SRAM area in the chip. Finally, we analyze compute bound applications. Applications in this class have high temporal locality and arithmetic intensity, low less first miss ratio, and MPKI. The low less first miss ratio MPKI and high temporal locality in this case indicates that such applications make effective use of the cache hierarchy and also have low memory intensity. However, contrary to Class 2B applications, the high arithmetic intensity indicates that such applications execute many operations per byte loaded from the memory hierarchy. You observe that the host performance is always greater than the NDP performance for the application in this class. We conclude that class 2C functions do not experience large memory bottlenecks and are not a good fit for NDP systems in terms of performance. To conclude, our scalability analysis leads us to 6 different classes of data movement bottlenecks that have been identified using 4 key metrics. We invite you to check our paper for a comprehensive discussion about the performance and energy scalability for each one of the memory bottleneck classes. Next, we aim to evaluate the accuracy of a workload characterization for a large set of functions. To this end, we apply step 2 and step 3 of our methodology, memory bottleneck classification, to the remaining 100 memory bound functions that we obtain from step 1. Then we perform a two-phase validation to calculate the accuracy of our workload characterization methodology. In phase 1 of our validation, we calculate the threshold values that defines the low-high boundaries for each one of those 4 metrics that we use to cluster the initial 4 applications in the 6 memory bottleneck class. We also include the last first miss ratio curve slope to indicate when the last first miss ratio increases, decreases, or stays constant as we scale the number of cores. In phase 2 for validation, we calculate the accuracy of a workload characterization by classifying the remaining 100 memory bound functions using the threshold values you obtained from phase 1 and then last first miss ratio curve slope. After phase 2, a function is considered to be currently classified into a correct memory bottleneck class if and only if it fits the definition of the assigned classes using the threshold values obtained from phase 1 and follow the expected performance trends of the assigned class when the function is executed in the host CPU system and in the NDP system. By applying our such validation methodology, we find that we can currently classify 97% of the 100 memory bound functions into one of the 6 memory bottleneck classes. We expect that such accuracy of our methodology can be further improved by incorporating more workloads into our workload suite and fine-tuning each metric to encompass an even larger set of applications. So we have much more analysis and in our paper that are not here in this presentation, which I'm going to list next. So for example, we have a study where we evaluate how increasing the size of the last level cache impacts our workload classification, from where we observe that very large L3 caches can mitigate some contention bottlenecks. We also have a summary of our workload characterization methodology, including workload characterization using in other host and NDP cores. We discuss the limitations of our methodology, and we have analysis of the diversity of our benchmark suites. All of this in our paper, the full draft of our paper. Finally, I'm going to briefly talk about the case studies that we have in our work. There are still many open research questions related to the data processing, as for example, how to design good interconnects for new data processing systems, how to develop data mapping allocation that can fully leverage the NDP system characteristics, how to design effective NDP cores architectures, both related to accelerator or general purpose cores, what is the correct or the most appropriate floating granularity of NDP for NDP for a particular application, how to program any data processing system, how to do coherence in the data processing system, now in a mix the data processing system and host system, how to apply system integration between a host and CPU system, and much more. So if you still want to do a PhD in processing memory topics, just pick your favorite topic and go for it. There is still a bunch of open topics that we need to address. So our goal in this case study is to illustrate how our benchmark suite is useful to study some of such system open research questions in the data processing development. So we present 4 case studies in this paper. In the first case study, we use the DAMOVE benchmark suite to evaluate the interconnect network overhead that NDP cores placed in different vaults of a 3D stack memory suffers from. We observe that a large portion of the memory requests NDP core issues go to remote vaults, which increases the memory access latency for the NDP core. We believe that the move can be employed to study better data mapping techniques and interconnect networks designs that aims to minimize the number of remote memory access that the NDP core executes, and also the impact of the interconnection network on the memory performance, and the application performance, sorry. In the second case study, we evaluate the benefit that NDP accelerators can provide for 3 applications from our benchmark suite. We compared the performance improvement of NDP accelerator provide against the computer-centric versions of the same accelerator. So we observed that the NDP accelerator provides significant performance benefits compared to a compute-centric accelerator for applications in class 1A and 1B. So those are the bandwidth-bound applications and the latency-bound applications. At the same time, it does not prove performance for applications in class 2C, which are compute-bound. We believe that the move can aid the design of NDP accelerators that target different memory bottlenecks in the system. In the third case study, we performed an ISO area and power performance evaluation to compare the NDP system using in-order and out-of-order cores. We observed that in-order cores performance benefits for some applications are limited by the core's static structure and scheduling mechanism. We believe that bare NDP systems can be built by leveraging techniques that enable dynamic structure and scheduling without incurring the large area overheads and power overheads of out-of-order cores. The move can help in this analysis and development of such NDP architectures. In the fourth case study, we evaluate the benefits of offloading small portions of code, for example, a basic block, to an NDP system, which simplifies the design of the NDP core. We observed that for many applications, a small percentage of basic blocks is responsible for most of the last level cache misses. By offloading these basic blocks to our NDP core, we observe a performance improvement of up to 1.25 times of that of the baseline system. We believe that the move can be used to identify simple NDP structures that can enable building efficient NDP systems in the future. Next, I'm going to dig a little bit deeper into one of those case studies. In this case, the NDP accelerator case study. So the goal of this case study, as I said before, is to evaluate compute-centric versus NDP-centric accelerators. So we define as a compute-centric accelerator a custom accelerator that access DRAM using our off-chip interconnect. This is similar to your regular, for example, edge TPU accelerator or neural network accelerator. We contrast this as compute-centric accelerator with a neat data processing version of the same accelerator. So you take the compute-centric accelerator, the custom accelerator, and we move it to the logic layer of a 3D stack system, and we compare both systems. It's important to say that in both configurations, the custom accelerator is exactly the same. The only thing that changes is the bandwidth and latency available for each one of the system configurations. So we make we compare such accelerators using 3 applications for our benchmark suite. Here in this plot, I have applications for class 1A, which is a neural network application, for class 1B, which is a linear algebra application, and for class 1C, which is also a linear algebra application. Class 1A, again, is memory-bound, DRAM bandwidth-bound applications, 1B, DRAM latency-bound applications, and 2C, compute-bound applications. And the y-axis, we have the speed up over the compute-centric accelerator. So based on that, we make the following observation. So you see that the compute-centric version of the NDP accelerator heavily outperform the compute-centric accelerator for applications in class 1A. It modestly provides performance improvement for applications on class 1B and provides exactly the same performance of applications in class 2C. So therefore, we conclude that the performance of the NDP accelerator are in line with the characteristics of the memory bottleneck classes, meaning that applications that are the applications that are classified as DRAM bandwidth bound and DRAM latency bound using general proposed NDP systems are also DRAM bandwidth bound and DRAM latency bound using accelerator-based system. Therefore, analysis or memory bottleneck classification can be applied to study other type of system configurations other than only general proposed NDP or host systems. For a more detail on all of those case studies, we invite you to check our paper. So we open source our benchmark suite and or the move to chain on our Safari GitHub. Over there, you can find the DAMove benchmark suite and also the DAMove simulator. All of that is open source, and you can get it in the following link. So now I'm going to conclude the talk. So as the key problem that this whole work is trying to solve is that even though that we know that data movement is a major bottleneck in modern systems, it is still unclear how we can identify in a systematical way how the different sources of data movement bottlenecks and correlate these data sources of data movement bottlenecks with the most suitable data movement mitigation technique. Therefore, the goal of this work is to design a methodology to identify sources of data movement bottlenecks and also to compare compute-centric and memory-centric data movement mitigation techniques. The key approach that we take is to perform a large-scale application characterization to identify key metrics that can reveal the sources of data movement bottlenecks. The main contribution of this work, we have 4 main contributions of this work. The first one being the experimental characterization of 77,000 functions across 204 applications for varying domains, which we use to drive the methodology that can characterize applications based on data movement bottlenecks and their relation with different data movement mitigation techniques. We applied this methodology and we collected its result in a new benchmark suite called DAMove, which is a benchmark suite with 144 functions designed to the study of data movement bottlenecks. We developed 4 case studies to highlight how our benchmark suite can be applicable to open research problems or in data processing. Again, DAMove is open source and you can get it in your GitHub. So thank you so much for listening, and I would be glad to take any question if there is any.
Thank you very much, Geraldo.
Thanks, Juan.
I don't know if there are any questions from our students. If not, I would like to ask you something, Geraldo, and also I would like you to comment on some discussion we had in the YouTube chat. But yeah, first of all, the question I wanted to ask you. So, how far is this DAMove tool from being applicable to real-world systems, real-world PIM systems, like, for example, UpMem or HPM PIM that you mentioned in the beginning of the talk?
I see. So I think for UpMem, we can easily apply it because if you abstract the programming model of UpMem, for example, the data processing architecture that was used in this system quite resembles the architecture that of the UpMem system itself. So you use both out of other cores and in other cores and accelerators in your data movement in this paper to evaluate data movement bottlenecks. And the in other core setup is really similar to the UpMem setup. So we have simple in other cores connected to some scratchpad memory. In the case we use caches in this paper, and also through memory channel that provide high bandwidth for the NDPIN core. So in that case, it's quite similar. For other architectures like FIMDRAM, for example, HBM, or more neural network centric ones like the Alibaba one or the SK Hynix one, is a little bit different. Fundamentally, it's not so different because if you just care about data movement bottlenecks, meaning identifying if application is bandwidth bound or latency bound, you could still use that move to figure out if the application is bandwidth bound and latency bound, and then map this application to one of these architectures. But if you want to further fine tune, let's say, your decision of suitability of NDP for that particular architecture, would require further studies, because in that particular case of those architectures, those are near DRAM bank. So the amount of parallelism is much larger, but at the same time, the restrictions on hardware that you can put is much more strict. So there is still a next step that needs to be done to let's say apply this DAMove methodology over other types of data processing I don't want to say paradigm, but system organization, let's say, and to nail down even more the decision of taking application, if it would benefit for that system or not. So I hopefully it answered the question.
Yeah, I think so. And how about the simulator? Do you think the simulator is, I don't know, configurable or can be easily configurable to
Good question.
be more similar to existing architectures?
Yeah, the simulator is quite flexible in that sense. So in Romulator, for example, so Romulator itself is already extremely flexible, and ZSim is also quite flexible. So since both of them provides really large flexibility, it can be, I don't want to say trivial, but it's somehow simple to modify the organization of the simulator to simulate these different organizations, like the HBM pin, for example. What can be a little bit tricky is to replicate the programming model that these particular pin systems are employing. Because some of them, for example, the HBM pin uses some TensorFlow backends. So and the simulator is targeting 886 ISA, but there are also tricks that you can employ to mimic the same type of ISA that these HBM pin architectures, for example, are going to be executing, because in the end, it's just it's just memory activations and memory precharges that are being translated in issue to the memory to the pin accelerator itself. So which is already heavily supported by your simulator. So just need some applying some tricks in the front end, let's say, so we can have this to solve this gap between the programming model itself. So yeah, so definitely the simulator could be adopted for studying these other systems.
I see. Yeah, thank you very much, Geraldo. And actually related to that, and I want to connect what you just said to this discussion that we had in the YouTube chat, because one person asked about how to maintain coherence between the memory side, between the pin side and the host side, right? So this person was asking himself whether, I mean, what do we have to do with, for example, prefetchers or with speculation in the host processor? So how this could affect the idea of offloading computation to the memory, right? In my answer, I mentioned that one possibility, as actually this person suggested himself, is make the area that is going to be accessed by the pin cores uncatchable, or at least do it temporarily. I suggested him to take a look at the Conda paper as well, and I mentioned other potential solutions, like for example in PIM-enabled instructions, where the amount of memory that is being accessed by every individual instruction is very small, either one cache line or two cache lines. So it's relatively easy or possible to keep track of where the cache lines reside, and based on that, the schedule on the right place. In the end, processing in memory is not only processing in memory, is processing where it really makes sense, right?
Yes.
And I think that your simulator and your benchmark suite can be also very useful for these kind of studies, as you actually mentioned in one of the slides. I think it was slide 60. But anyway, if you want to comment or add anything.
Yeah. So coherence is always a kind of a problem, not a problem. There are different approaches to handle coherence, right? So making a region of the memory uncacheable is that's I guess the most easy solution, but it can highly impact the performance of the entire application, not only that particular code that you are executing, because there are since the application goes through phases during the execution time, if you statically let's say that some memory region is uncacheable in the hopes of offloading to process memory. So if you always offload, it's fine. There is no you're going to gain, right? You're never going to get anything in the cache, so it's fine to put the region uncacheable. But there are many works that is not the case. So application goes through phases, and in a particular phase, a particular regional code is suitable for NDP, and the other one is not for. And in the moment that the application is not suitable for NDP, the data is not going to be on the cache and could be in the cache, and then you have to go to the memory, and you're going to create some overhead for the overall execution time. So they are like, for example, if I'm not mistaken, the HBM pin solution, for example, employ. Am I correct? I think I'm correct. Employ some region of memory. They set some region of memory as uncacheable for the execution of the machine learning kernel that they are going to execute. In that case, it's easier because the application is kind of they are designing the system for that particular application. They know the application. They can do whatever makes more sense in that setup. But for general purpose, is much harder. General purpose acceleration. As Juan said, that from our group ourselves, we have been working on coherence work. So we have 2 papers, LazyPing and Conda. Those two approaches maintains they maintain speculative coherence between the whole system and the CPU system. Sorry, I said the same thing. The whole system and the NDP system, and that is one solution, but it's not definitely it's not the ultimate solution for this. And API also is really good idea because but in the case the excess granularity needs to be small, right, to maintain the coherence. So yeah, so and that is also the problem of maintaining coherence between the pin cores. So I have a system that is really high. If you have an NDP system with has many cores, like the MCC, for example, it can becomes a nightmare if you allowed all of the NDP systems to view the whole to see and to address the same virtual memory space or the same memory space. It can become really hard to figure out. And there is, of course, some caching system being employed to figure out if a particular piece of data can be accessed or not by a particular pin core, because employing the same coherence protocols that we have in the CPU, like directory base or snooping base in the NDP system, is quite costly because of the area limitation that you have of design a network or type of thing. So yeah, so there is these 2 problems, both from the host parts to the pin cores and also across pin systems, pin cores themselves. So yeah. And definitely our benchmark suite can be employed to studying this. We right now we have a base MESI protocol that comes from ZSync over there for coherence, and also we have a simple bypass read-only type of protocol. It's not a coherence because then you only read from the cache. But yeah, we have a simple modifying pretty naive coherence model for the process memory cores. But that model could also change to other fancier coherence models also.
Okay, yeah, I see. Yeah, I guess your answer makes sense. I think that also it's important to keep in mind here that universal solutions to all these problems might be difficult, because in the end, processing in memory is not just a specific device, right? Yeah. And if we think about the type of processing in memory system that you evaluated here and compare it, for example, to the PEI system that we mentioned, I think it's there are like clear differences, and they call for different solutions to specific problems or yes, or specific issues like the memory coherence, as you said. But anyway, yeah, thank you very much, Geraldo. I think there was a very good talk, and thank you very much for your answers as well.
Thanks, Juan, for having me.
Yeah, of course. hopefully we will have you soon as well.
Yes.
in an upcoming lecture. So yeah, if there are no other questions, I cannot see any additional questions in the YouTube chat. We already left several links to papers, related papers, to your DAMOVE paper, and also to the DAMOVE repository that's freely available to everyone. So yeah, thank you very much. And I guess we are done for today. And I hope to see everyone in our next lecture in this BIM course next Thursday.
Bye
Bye-bye.